experiments after having controlled dependent variable and independent variables to check what is the mean of the y or the mean of the dependent variables across different experiments or across different scenarios. So in an experiment design, the independent variable may be either a treatment variable or classification variable. So this is just a terminology. We call independent variable in experimental design a treatment variable or classification variable, because experiments are classified by types of independent variables or independent factors used to influence the y, and we need to conduct experiments on y depending on the factors under study. So a treatment variable is also a variable the experimenter controls or modifies in the experiment. So this is also another terminology where the treatment variable is variable which is controlled or modified during the experiments. A classification variable, another definition, a classification variable is a characteristic or experimental subject that was present prior to the experiment and is not a result of the experimenter's manipulation or control. So the classification variable is a variable that exists before the experiment or use it as reference model or as a reference experiments to check how the response variable, which is y, has been modified and need to be compared to the treatment variable, to the classification variable, which is happening before the experiments. Independent variables are sometimes referred as factors. So factors that used to influence the y, or the factors to which the y or the dependent variable is used to respond. Okay, any questions regarding these definitions? So these definitions are just needed for experiment purpose to check how y responds to x's or to various x's depending on situations or scenarios. So let's define a completely randomized design. A completely randomized design is what we call one-way ANOVA. So subjects are assigned to randomly to treatments. Under this scheme, subjects are assigned to randomly to treatments. The experiment contains only one independent variable with two or more treatments levels or classifications. So let's suppose data analysts decide to analyze the effects of a machine operator on the value opening measurements of valves produced in manufacturing plants. So the independent variable in this design is the machine operator. Suppose further that four different operators operate the machines. These four machine operators are the levels of treatments or classification of the independent variables. So the dependent variable is the opening measurement of the valve. So we got four machines. 1, 2, 3, 4. We got machine operator, okay? And under each machine, we got some measurements, valve opening measurements. So this is machine 1, machine 2, machine 3, machine 4. Machine operator is called independent variable. The machine number is called classification levels. Under each classification level, we got some measurements. Measurement number 1, measurement number 2, measurement 4, and measurement n. So we got the valve opening measurements, which are called dependent variables. So under each classification level, 1, 2, 3, 4, we got a set of dependent variables or valve opening measurements. So this is the example numerically represented in this table. So we got the machine operator. Machine operator is the independent variable. We got classification level 1, level 2, level 3, level 4. Under each level, we got some measurements. So we got 1, 2, 3, 4, 5 measurements from level 1. We got 1, 2, 3, 4, 5, 6, 7, 8 measurements from level 2. We got 1, 2, 3, 4, 5, 6, 7 measurements from level 3, and we got 4 measurements from level 4. Classification level or levels are simply the experiments. We got one machine operator performing collecting measurements under 4 different classification level or experiments. Classification level is simply the experiments. So machine operator is taking measurements or is recording measurements under each different level of experiments. Okay? So in general, if case samples are being analyzed, the following hypotheses are being tested in one way or another. So under the null hypothesis, mu1 is equal to mu2, mu3 is equal to mu k, where mu is the mean of measurements. At least one of the means is different from others. So we got experiment 1, experiment 2, experiment 3, experiment 4. Under each experiments, there are some measurements. Measurement 1, 2, 3, 4, k. For experiment 2, we got measurement 1, 2, 3, and k. So, and we need to calculate the mean under each measurement, 1, 2, 3, 4, and we need to check if the mean of measurements under experiment 1 is equal to the mean of measurements under experiment 2, is equal to the mean of measurements under experiment 3, is equal to the mean of measurements under experiment 4. Okay? So the purpose is to analyze all sample means at one time and to build up errors rates. This design is completely randomized, meaning that measurements should be taken and measured in a random way. Some assumptions related to these experiments or to these hypothesis tests should be notified or observed. First one, observations are drawn from normal distribution. So these observations of measurements under each experiment should be randomly generated and observed. Observations represent random samples from populations. So measurements should be random variables. Third, the variance of the populations are equal, meaning the variance of measurements under measurement 1, experiment 1, is equal. So the variance of this vector of these measurements is equal to the variance of these measurements, is equal to the variance of these measurements, is equal to the variance of these measurements. This is a very strong assumption. Two strong assumptions Observations should be drawn from normal distribution. This is very strong assumption. And second assumption is that the variance of measurements is equal across all experiments. Experiment 1, experiment 2, experiment 3, experiment 4. Questions regarding this? Okay. Now look at some definitions. This is a recall from previous previous lectures dealing with linear regression. Let's define total sum of squares. Total sum of squares can be broken down into two components: treatment sum of squares and error sum of squares. So total sum of squares is composed of two major elements: the treatment sum of squares and error sum of squares. Now, we need to perform the test, Fisher test, to test the null hypothesis that mu1 is equal to mu2 is equal to mu3 is equal to mu k, where mu is the mean of measurements under experiment 1, mu2 is the mean or average of measurements under experiment 2, mu3 is the mean of measurements under experiment 3, and mu k is the mean of measurements under experiment k. In the previous example, k is equal to 4 because we got 4 experiments: 1, 2, 3, 4 experiments. So the null hypothesis is that all experiments are having the same mean. The alternative hypothesis is the following: at least one of the means is different from the others. One of the means is different from the others, meaning at least mu1 is different from mu2, mu3, mu k, or mu2 is different from mu1, mu3, mu k, or mu3 is different from mu1, mu2, and mu k, or mu k is different from mu1, mu2, and mu3. So we need to calculate Fisher tests or Fisher statistic. This Fisher statistic from the previous example is equal to 10.18. How did we get the 10.18? So Fisher is equal to MSC over MSE, where MSE is sum of squared errors over degrees of freedom of E, where degrees of freedom of E is equal to N minus C, where N is sample size and C is the number of treatment levels, for example, 4. MSC is equal to SSC. SSC is total variation over DFC, where DFC is number of experiments minus 1. DFC is number of experiments minus 1. So we got MSC. We got MSE doing calculating the ratio of these quantities. We got the F, where F is equal to MSC over MSE. By the way, by using SAS, when you apply this one-way ANOVA, when you go to SAS AG and call for one-way ANOVA function or table, you need to define the variables, define one-way ANOVA, and you run the test. When you run the test, you get this exactly the same table. You get F and you get the p-value of f. The p-value of f will help you to accept or reject H0. If p-value of f is larger than 5%, then accept the null hypothesis H0. If p-value is less than 5%, then reject H0 and accept the alternative one, meaning at least one of samples, one of the averages is different from the others. From this example, the calculated p-value is 0.003, which is less than 5% significance level. So do we accept or reject H0? What do you think?
We reject the null hypothesis.
Yes, because of the p-value of f is equal to 0.003 less than 0.05, you reject the null hypothesis of equality of means and accept the alternative one, meaning that at least one of experiments is having an average different from one of the others. Okay? With PARISA tonight, you will see applications of one-way ANOVA by using SAS-EG. Another example, automobile juries. So injury claims, this fire injury is having data from 1984. From 1986, cars are listed in table 9.1, in injury 9.5, for cars in following categories. We get some set of categories: small two-door, mid-sized two-door, large two-door, small four-door, mid-sized four-door, large four-door, small station, wagons and vans, mid-sized station wagons and vans. So we get a kind of 1, 2, 3, 4, 5, 6, 7, 8, 9 experiments. We got 9 experiments. The variable car class is used to indicate into which category each car falls. So the categories are coded from 1 to 9 in the order shown, in this order. So this is the data set. So we got different car names, we got the corresponding car class, and we get the number of injuries. And the purpose is to check if the average injuries is similar across car classes. We got 9 car classes, we got a number of injuries by car classes, and we need to check whether or not the average car injuries is similar across all car classes. So in ANOVA terminology, the dependence variable is injury. The dependence variable is injury. One concern is whether the average number of injuries differs from the 9 different categories or populations. So meaning that we need to check if the average average number of injuries is similar across all classes from 1 to 9. The data comprises 9 samples from each of these 9 populations, and explanatory variable or factor is the car class. So the car class is the explanatory variable. ANOVA is designed to investigate the relationship between quantitative dependence variable, okay, and qualitative independent factor or variable. Because a car class is a qualitative variable, okay? The car class, this is the car class, are all 9 qualitative variables, and the dependent variable is the number of injuries, which is a real number. So this is the output from SAS, e.g. showing results from ANOVA analysis. So we got this class level information, we got the class, we get levels, and we get values. So the class name is car class. Levels, we got 9 levels. We got 9 levels from small to down to small to the door to large stations, wagons, and vans. We got values of car classes going from 1 to 9. And the number of observations is 12. We got the dependence variable in jury. We got ANOVA table. This is the ANOVA table with F. This is F. The statistic F. This is the statistic F. This statistic F used to test the null hypothesis that average number of injuries is similar across all 9 classes versus at least one average is different from the others. So the F value of this test, Fisher test, is 22.80. The corresponding p-value is 0.0001. So do you think we accept H0 or we reject H0? Do you think we accept or reject H0? Look at p-value.
We reject HO.
Yes, we reject HO and accept the alternative hypothesis stating that at least one of the average is different from the others. We got another table, okay? Another table where we regress classes, where we regress the number of injuries on classes, and we got similar p-value. We got a similar p-value. So following the results, this p-value is equivalent to this p-value, to this one. The result is coming from the regression of injuries regressed on car class. You regress on car class. This is when applied. This ANOVA is dealing with one simple test, okay, or group. So now imagine we need to perform several tests and we need to check all of them. Sometimes the analyst is satisfied with conducting an overall test of differences in groups such as the one ANOVA provides. This is very important when you are facing different samples, different experiments, and you need to check differences across experiments. So when it is determined that there is an overall difference in population means, it is often desirable to go back to the groups and determine from the data which pairs of the means are significantly different. Meaning that when your results is indicating that you need to reject the null hypothesis, better for you to go back to the regression analysis or to the experiment, previous experiment, and check its appropriate or its corresponding p-value, whether or not is it larger or below 5%. Also, several techniques referred to as multiple comparisons have been developed to handle this problem. When you are comparing means of different examples, you need to perform a kind of multiple comparison tests. So, for example, consider a data set with 3 levels of treatments. So each type of multiple test can be used to compute multiple comparison tests between group 1, 2, and 3. So there are 2 kinds of tests, multiple tests. There is what we call Takey's honestly significant difference test and Takey-Cramer procedure. The first one assumes sample sizes are equal, and the second one assumes sample sizes are unequal. If your various experiments are showing different, similar size of experiences, then use Takey's honestly significant difference. Otherwise, use the second example. Takey test determines the critical difference necessary between the means of any 2 treatments levels for the means to be significantly different. So the software calculates HSD statistic along with a critical difference. Data analysts can examine absolute value of any of all differences between pairs of means. So the software calculates differences between all pairs of groups, and by doing that, the data analyst can test the null hypothesis that differences are across all pairs, and if it is rejected, the data analyst can look at the source of differences, meaning that where this difference is coming from. Is it between group 1 and group 2, or group 1 and group 3, or between group 2 and group 3? So the data analyst can find out the source of differences. The decision rule: if a pair of means is having, if pair of means is larger than HSD, then reject H0, equality of means for that particular pair of treatments. So simply look at the p-value. P-value less than 5%, reject H0, larger than 5%, accept H0. Takey-Cramer procedure: the rule, if a pair of means is larger than Takey-Cramer statistic, which is automatically calculated by the software, okay, then rejects H0, where H0 states that there is a kind of equality of means to be verified. Takey's HSD test. The SSD statistic is equal to Q alpha CM and C multiplied by root of MSE over N, where Q is a critical value of standardized range distribution, MSE is mean of squared error, N is the sample size, and you get your corresponding Takis HSD statistic. Takey-Cramer formula is this one, okay, and which is similar to the previous one, except we consider the breakdown of the sample because we got because we do not have similar variances. So the Takey-Cramer statistic follows a Q is a Q multiplied by root of MSE multiplied by 1 over NR plus 1 over NS, where NR is size of sample R and NS is size of sample S. Takey's HSD tests, sorry, we get plant 1, 2, 3. HSD test is equal to 0.88. We got the group means from experiment 1, group mean from experiment 2, and group means from experiment 3. And the statistic is simply average of mean 1 minus average of mean 2, average of mean 1 minus average of mean 3, average of mean 2 minus average is 3. The first difference of averages is equal to 3.8. The second difference of averages is equal to 3.4. And the third difference of averages is equal to 7.2. And the goal is to check whether the difference of x1 minus x2, mean of x1 minus mean of x2 is equal to 0, mean of x1 minus mean of x2 is equal to 0, mean of x2 minus mean of x3 is equal to 0. Because if x1 minus x2 is equal to 0, it means that x1 bar is equal to x2 bar. If x1 bar minus x3 bar is equal to 0, it means that x1 bar is equal to x3 bar. If x2 bar minus x3 bar is equal to 0, means that x2 bar is equal to x3 bar. So this is basically how test is performed. The software, for instance, SAS, we give you the HDS statistic, okay, which is 2.88 for each single test. So we reject H0 because mean of group 1 is equal to mean of group 2. So we reject H0 where mean of group 1 is equal to group 2. Why we reject it? Because the theoretical HDS is less than the calculated HDS. This is the calculated HDS. For the second experiment, we test the null hypothesis that x1 bar is equal to x3 bar. The corresponding HDS statistic is 3.4, which is larger than 2.88. Then we reject H0, and we accept that there is significant difference between the two samples, sample 1 and sample 3. For the last one, we test the null hypothesis that average of x2 is equal to average of x3. The difference is 7.2, which is larger than the theoretical value of 2.88. So we reject the null hypothesis that mean of group 2 is equal to mean of group 3. Any questions regarding this example? Okay, now look at randomized block design, okay, which is very similar to the completely randomized design. It focuses on one independent variable, the treatment variable of interest. But the randomized block design also includes a second variable. The second variable is the block-in variable. We call it BV, block-in variable. This block-in variable can be used to control for confounding or concomitant variables. So this block-in variable is simply used when you need to control for 1, 2, or 3, or 4 variables. Okay, the variables are those on rows, and experiments are those on columns, and the dependent the inputs or variables are those on rows. BV is simply a constant variable used to control for variable for dependent variable 1 or 2 or 3, etc. This is the example of randomized block design. So this is, we got a brand A, this is a marketing problem where we look at similarity in sales across different regions, across different geographic regions for different brands. So we got brand A, brand B, brand C, brand D, brand E, and brand F. And we got 5 regions: Vancouver, Toronto, Calgary, Saskatoon, and Montreal. So for each brand, we got sales occurred in Vancouver in each single geographic region. So the data analysis studies the cost of gas in Canada among urban areas. So it's not sales, it's profits of gas. The data analyst believes that there was a significant difference in average cost of a liter of gas among urban areas in different parts of Canada, namely Vancouver, Toronto, Calgary, Saskatoon, and Montreal. So he placed random calls to gas stations in 5 different cities. Vancouver, Toronto, Calgary, Saskatoon, Montreal. In addition, he realized that the brand of gas might make a difference. The brand of gas, because there are six brands of gas, A, B, C, D, E, F. So the treatment variable is cost of gas, blocking variable is brand, okay, and sample is 30 coils measurements. So all of these are 30 coil measurements. So we need to partition total sum of squares of variations. So the total sum of squares can be divided into two components: treatment of sum of squares and error sum of squares. The error sum of squares can be broken down into two components: block sum of squares and new error sum of squares. This block sum of squares is the error coming from blocks, and this one is the new error sum of squares. Here we got the formula to calculate F for treatments, Fisher test for equality of treatments, and Fisher test for equality of blocks. So the goal is to calculate the F statistic, one for treatments and one for blocks. For treatments, F of treatments is equal to MSC over MSE, where MSC is SSC over C minus 1. Okay, SSC is this quantity, this one. MSSR is this quantity, this one. C is the number of experiments multiplied by x minus xi, each single xi minus the mean of all groups, mean of each group minus mean of all groups. And for SSE is the number of calls or the number of observations, total number of observations multiplied by sum of mean of each experiment minus overall mean of all experiments. So you get F for treatments, you get F for blocks, where F of blocks is equal to MSR, where MSR is SSR over N minus 1, where N is the number of calls or observations. SSR is this quantity. All this stuff will be calculated automatically by SAS-AG, and you need to know what is the null hypothesis and what is the alternative one, and you compare a calculated p-value provided by SAS-AG compared against the reference or the threshold value of 5% significance level, which is equivalent to 0.05. So the hypotheses follow for the treatments. So these are the null hypotheses to be tested and decision rules. So we got null hypothesis for treatments, we got null hypothesis for blocks. For treatments, we got S0, mu1 is equal to mu2 is equal to mu3, mu4, mu5. Alternative one, at least one of the treatments means is different from the others. Okay? One of the treatments is different from the others, meaning that at least, so for the treatments, we need to check if the mean of Vancouver is equal to the mean of Toronto, is equal to the mean of Calgary, is equal to the mean of Saskatoon, is equal to the mean of Montreal. This is for treatments. For blocks, we need to check whether the mean of A, is equal to the mean of B, is equal to the mean of C, is equal to the mean of D, is equal to the mean of E is equal to the mean of F. So for treatments, we need to check if average across columns are equal, and for blocks, we need to check if means across rows are equal. Okay? Any question regarding this? So F for treatments is equal to MSCC over MSE, and F for blocks is equal to MSR over MSE. And the decision rule for treatments, if F calculated is larger than theoretical F, then rejects H0. Or if p-value is less than 5%, then reject H0. So H, and for both tests, for treatments and for blocks, H is 0 is rejected when the corresponding p-value is less than 5%. This is an example when we consider the design of serial packages. 4 packages design, which are treatments, are to be tested in 20 stores. The 20 stores are divided into 5 groups or blocks of 4 stores each by size. The treatments are randomized within each block and independently between blocks. So the table 9.5 shows the data in alternate form, SAS. So we got cells, we got size, we got the design, okay? And we need to check if mean of cells is equal across sizes, and also if and also if the means of cells is similar across design. We separate the hypothesis tests. This is very important. So ANOVA, this ANOVA table for SAS is set into 2 parts. The source of variations are labeled model, error, and corrector total. And the model variation is used to combine the information from both treatment and block into a single measure of quality of the model. Okay? So we got the class or groups, we got size, and we got design. For size, we got 5 levels, 1, 2, 3, 4, 5. For design, we got 4 levels, 1, 2, 3, 4. The number of observations is 20. So 1, 2, 3, 4. So from 14, 23, 17 to 7, 47 and 64, we got 20 observations or 20 records. This is the table for the source of variations, okay? Where source of variations are labeled model, error, and corrected total. And this is the model variation where it is partitioned or broken down into size and design. So we get a p-value equal to 0.0842, meaning that the source of variations, which are model, error and corrected model, following this, we conclude that the mean is equal across experiments. For the second one, which is the most important, we get the p-value for size is equal to 0.024, and the p-value for design is equal to 0.9506. So for this one, So this one tests the null hypothesis that cells are equal, average of cells are equal across size. The obtained p-value is equal to 0.024. So we reject or we accept the null hypothesis of equality of means across size. Do we accept or reject? Since the p-value is less than 5%, you reject the null hypothesis that the mean of cells is equal across sizes. Now let's look to this one. This one tests the null hypothesis that the average of means is equal across designs. The p-value, the corresponding p-value, is equal to 0.9506. So we accept the null hypothesis that the mean of cells is equal across design. So the mean of cells is not equal across size, but it is similar across design packages. It is similar again across design packages. So mean of cells is not different, okay? Is not different, is equal across design, but it is not equal across size. In a question regarding this table, this is the most important one. This table is very important. You can check, you can split equality of means across size and across design. For size, the null hypothesis is average of cells is similar across all size packages 1, 2, 3, 4. The alternative one, it is not. At least one is different. A p-value is 0.024, less than 5%, suggests that H0 is strongly rejected. And we accept the alternative one, meaning that at least one of averages of cells is different across sizes. For design, the null hypothesis is that average of cells is equal across all design packages. The alternative one is at least one is different. Since p-value is equal to 0.95, larger than 5%, we accept the null hypothesis. Any question regarding this? Okay. So we have determined whether there is difference in cells because of package design. So H0, mean in package 1 is equal to mean in package 2, is equal to mean in package 3, is equal to the mean in package 4. Alternative one, all treatments effects are not equal. So the null hypothesis cannot be rejected. There is no evidence of a difference in cells because of package design, because of size. Sorry, because of design. But it is rejected for size. It is rejected for size, but not rejected for package design. Any question regarding these results? Two-way ANOVA. In two-way ANOVA, we got two or more treatments, meaning that we got two or more independent variables are explored in a simultaneous manner. Advantages: you save time and possibility of investigating interaction terms. So, like the previous one, we got treatments in columns, and we got treatments also in rows. And we need to check if means across columns is equal, and also we need to check if means across rows is also similar, is different or not. So in this example, the dependent variable is stock price. Independent variables are volume, where volume take three levels: high, low, moderate, and prime interest rates. Prime interest rates takes also two levels: up, down, and same. Advantage of two-way ANOVA when applied to this financial problem follows: the data analyst can determine whether share prices changes are different under various level of volume, under various level of prime interest rates, and under interaction between volume and prime interest rates. Very important in finance and also in marketing to check the effect of interaction terms. So ANOVA is used to analyze data obtained from categorical design. So for factorial design with two factors or two independent variables, two-way analysis of variance or two-way ANOVA is used to test the null hypothesis, following two hypotheses. For row effects, column effects, interaction effects. So for row effects, row of means are equals. Alternative one, at least one row mean is different from the others. For column effects, columns means are all equal. The column of the means of columns are all equal. Alternative one, at least one of the column is different from the others. Now, the beauty with two-way ANOVA is adding interaction effects. The difference between one way and two ANOVA is the inclusion of interaction effects. Under one way, there is no interaction effects, but under two-way ANOVA, there is interaction effects. For interaction effects, H0, interaction effects are 0. Alternative hypothesis, an interaction effect is present. So F values are determined for three effects. For row effects, for column effects, interaction effects. So F statistic and its corresponding p-value is calculated by SAS-AG or software for row effects, for column effects, and for interaction effects. So these are the formulas used to calculate F for rows, R for columns, and F for I, where I denotes interaction effects. You got FR is equal to MSR over MSE. FSC is for columns is equal to MSC over MSE. and for interaction effects is equal to MSE I over MSE, and to cut the corresponding quantities shown in this in this table. The calculations, by the way, are done automatically by the software. You need just to look at p-values of FR, p-value of SC, and p-value of FI to accept or reject the corresponding H0. So the formulas for rows, for columns, for interaction effects. So for rows, for rows, if F calculated is larger than theoretical F, reject is 0. Or if p-value is less than 5%, then reject is 0 and accept alternative 1. In this example, we got sales, we got price level. For price, we got for stock price, we got 3 levels. We got 2 levels, 1 and 2. And advertising, we got 3 levels, 1, 2, and 3. And we want to check if the mean of sales is similar across price levels, if it is similar across advertising level, 1, 2, 3, and if it is similar across interaction effects. So please look at this table. Sorry. Look at this table. This is the p-value for price, meaning that the mean of sales is equal across all price levels, okay, where price has 2 levels, 1 and 2. This is the p-value for advertising for the null hypothesis, stating that mean of sales is equal across all advertising levels, where levels of advertising is coming from 1 to 3. And the red one is the p-value associated with testing the null hypothesis that mean of sales is similar across all price advertising interaction effects. So meaning whether or not interaction effect has an impact on sales or not. So for price level, the null hypothesis is rejected because p-value is equal to 0.0161, less than 5%. So the null hypothesis of equality of sales across price level is rejected, meaning that one source of level is different for price. For advertising, we get p-value is equal to 0 less than 0.0001, which is 0. So it is less than 5%. So the null hypothesis of equality of sales, means of sales across advertising level, where advertising level is going from 1 to 3, is different. So this null hypothesis is rejected and alternative 1 is accepted, meaning that at least one level of advertising is having mean different from the others. For interaction effect has nothing to do with average of means, meaning that interaction effect is not affecting average of sales. So please do run two-way ANOVA only if you expect that interaction effect matters. If you do not expect interaction effect has a real impact, significant statistical impact on your Y, so do not apply two-way ANOVA analysis. stick with one-way ANOVA. So the only advantage of applying two-way ANOVA is the inclusion of the interaction effects. Otherwise, there is no interest. This is the two-way ANOVA in mathematical form, where y is the dependence variable, mu is the constant, alpha y is the effective factor A given level I, beta is the effective factor B, alpha beta is the interaction effect, and E is the error, and two-way ANOVA is very similar to running a regression model of y, the dependent variable, on a fixed mean, fixed constant, and and on effect A, effect B, plus interaction of effects A and B, and we got an error term. It's very similar to regression analysis. Testing for factor A effects, the null hypothesis is that alpha 1 is equal to alpha 2 is equal to alpha 3 is equal to alpha n is equal to 0. Alternative 1, at least one of the alphas is different from 0. Testing for factor B, for example, let's call A is the price level and B is advertising level. And for B, the null hypothesis is beta 1 is equal to beta 2 is equal to beta n. HA1, at least one of the B's or the betas is different from 0. For interaction effects, the null hypothesis is that no interaction between A and B exists, meaning that all alpha B's, alpha beta is equal to 0. Alternative 1, at least one alpha beta is different from 0. So this is what is represented in this table. Exactly the same thing. And you have just to look at the p-values, compare against 5% statistical significance level. If less than 5% rejects H0, if not, accept H0. So Y is says this is the common intercept, which is mu. Alpha is the coefficient for price. Beta is the coefficient for advertising. Alpha beta is the coefficient of the interaction effect, price advertising. When applied to experiments I and G, and we got the p-value for price, p-value for advertising, and p-value for interaction effects. P-value is less than 5%, which is suggesting that price level, advertising level, and price advertising interaction effects are all significant. An equation regarding this now let's look some representations of interaction effects. So this is an example where the two lines are almost parallel, which indicates a complete absence of interaction levels. So this is cells. We got beta 1, beta 2, beta 3. Okay, the two lines representing alpha and beta are quasi-parallel, so they are not interacting. It means that there is no interaction effect. For this one, if there were no differences in factor A effects, the two lines drawn would nearly coincide. Okay, so the effect is very marginal. For this one, here the two lines are not parallel, but they do not cross. So in this case, the interaction does not appear to be serious, or there is a kind of interaction level, but very insignificant, because the two lines are not connecting, are not crossing. For that one, if there were no difference in the factor of B effects, the two lines drawn would be nearly horizontal. So there is a kind of effect, but very, very marginal. In equations, the lecture is done. It is complete. If you do have equations, please ask me. So keep in mind that the main advantage of two-way ANOVA is just to investigate whether or not the effect of price of interaction effect is significant. So in experiment design, if you suspect that interaction effect matters, then use two-way ANOVA. Otherwise, there is no need. If you do have questions, please ask me. Okay, so please do not miss the tutorial with Parisa. You do have a tutorial with Parisa, and we meet on Wednesday, and Wednesday we will discuss a little bit your projects. Okay, if you want to meet with me in private, drop me an email to meet and discuss your project in a private way. So see you Wednesday, and do not miss a tutorial with Parisa.